Now in problem number 29, in section 6.1, we're supposed to find the values that make this expression undefined. Now we know an expression will be undefined, and this is an expression, right? There's no equal sign here, so it's just an expression, a set of computing instructions, but you can't just put any number at all into a set of computing instructions. Sometimes you put something in and nothing comes back out. So this is going to be undefined when the denominator is 0. So what's going to make this 0? So what we're looking at doing is this. Let's take this x squared minus 5x plus 4, and we're going to think of that as being 0. This is just a quadratic equation. We can factor this, and we're going to get x and x, a 5. Let's use a 4 and a 1, a minus and a minus. So we'll solve this equation getting a 4 and a 1. So if we put in a 4 or a 1 back in here, we're going to get 0. Now this is what we're doing. We're probably going to do this kind of in our head, but the way I'm going to write this problem, when I see this problem, I would write it like this. 5x plus 3 over x squared minus 5x plus 4. I'd rewrite it, 5x plus 3, and then I'd factor the denominator, getting x and x, get our 4 and the 1, a minus and a minus, and then from the denominator I can see, right, I'm really seeing this, but I can see now that what we want here is we need to exclude 4 and 1. So the question asks us to identify the values that make this undefined, and the values are 4 and 1. Now this problem asks us again to find the values for which the expression is undefined, but expressions we know are undefined only when the denominator is 0. This denominator is 5. It's never 0. So this expression here is never undefined. So this is never undefined, or they're asking us to find the values for which the rational expression says undefined. You know, I would just say there are none. This is defined for all numbers. You can put any number into this expression and compute and get a real number back out. What values are going to make this expression undefined? Well, I'm going to say none. I think that there are none here, and here's my reasoning. An expression is only undefined when the denominator, the bottom, is 0. Now look at this. No matter what you put in here, pick any number at all. If you pick 0, 0 squared is 0, you get 7. If you pick any other number and square it, it becomes positive. And a positive number plus 7 is positive. There is no way that this can ever be 0. Right? What you're kind of thinking is this. Y squared plus 7 being 0, or y squared equaling negative 7, we're not squaring any numbers and getting a negative. So there's no real numbers that make this thing here equal to 0. So we're going to conclude there are none. Now a little bit different here in 39. We're supposed to reduce this rational expression. So I've got an expression here. This is a set of computing instructions. What we're trying to do is make it more compact, more efficient. So right away I can see that what we're doing here is we're multiplying by y minus 2, then dividing by y minus 2. That is inefficient. So what we're going to do is we're going to divide out y minus 2. So y minus 2 into y minus 2 is a 1. Sometimes what we say is that we're going to cancel. And you can think of it as this. We're going to cancel this inefficiency. So when we draw this line, we're really getting a 1 here. Now, then we're left with 25 over 15. Well, both those are divisible by 5. And if we divide the top, the 25, by 5, we're left with 5. But then also times this 1. So 5 times the 1. And then in the denominator, the 15 divided by 5, that's the 3. And then also times the 1, times 1. So we're left here with 5 times 1 is 5, over 3 times 1 is 3. So this expression, the original, reduces to 5 over 3. Now this 5 over 3, this only works as long as y is not equal to 2. Right? Because if y is equal to 2, we're going to get something that is indeterminate. If we put a 2 in here and a 2 in here, we'll get 0 over 0. That's indeterminate. So we don't want divisions by 0, so let's exclude 2. So y is not equal to 2. So as long as y is not equal to 2, we're going to get 5 over 3. If y is equal to 2, this whole thing is not defined. Now in problem 41, here's an expression, a set of computing instructions, that once we know the value of s, we could put s into here and compute. But there may be, and there is, you can see it here, an inefficiency. What we're doing is we've got an s plus 9 on the top and 2 of them on the bottom. So we're multiplying by s plus 9 and then dividing by an s plus 9. That's inefficient. So what we're going to do is cancel one of these s plus 9. So there's an s plus 9 here and an s plus 9 here. We'll cancel the one with the top, one with the bottom. And what that's going to do is leave us with this s plus 9, this s minus 9 on the top, and on the bottom it'll leave us with, there were 2 down here, we removed one of them, so we're going to be left with an s plus 9. And we're going to say we can do this as long as s is not equal to negative 9. Right? Because if s is equal to negative 9, this thing is 0, and the whole thing is undefined.